So for question 14, we're given the statement that the magnitude of the vector A plus the vector B is equal to the magnitude of the vector A plus the magnitude of the vector B. And we need to explain this geometrically. Well, what does this statement mean? Well, we've got two vectors, and let's see what we can draw. If we had, say, the vector A there, and then we add on a second vector, let's call that the vector B there. If we wanted the path of A plus B, this would be this direct path here of A plus B. Now, does this picture match what we have here? Well, if we look at the length of A, if we were to add on the length of B here, it cannot possibly be the same as the length of this straight line here. Okay? So in other words, for this case, the magnitude or the modulus of the vector A plus B is not equal to the magnitude of A plus the magnitude of B. So they do not, and what's happening, they do not lie in the same direction there. So they're lying in A and B lie in different directions, so it can't possibly be the same. Well, let's look at the alternative case then. What about if they are lying in the same direction, such that again, we've got the vector A, and then we add on our vector B in the same direction. Well, how would we represent A plus B? Well, we can represent that like this, of A plus B. Well, let's look this time. Well, if we take the length of A and we add on the length of B, well, clearly they must be the same length. A plus B must be the same as the length of A plus the length of B. So in this case, we do have that the modulus of A plus B is equal to the modulus of A plus the modulus of B. So what does this mean? The vector, or the vectors A and B must lie in the same direction. And that's what this statement means. Now, you don't have to show the case where it's not, you don't have to graphically show why, but it gives you an idea as to why this works, but they are looking for this statement there. That's the important part. Now, moving on to II then, we're given a new situation. We've got the magnitude of the vector m is 3, the magnitude of the vector m minus n is equal to 6, the angle between the vector m and the vector n is 30 degrees. We want to find the angle between the vector m and the vector m minus n, giving your answer in degrees to one significant figure. So we've got a little bit to work out here. Diagrams are going to be the key so you can piece this together. Let's look at this statement. The angle between m and n is 30 degrees. So let's put on a vector m, and let's put on a vector n, and the angle between those is 30 degrees. Well, really in this problem, we're not so much looking at the vector n as we're looking at the vector minus n, because we really care about the resultant, which in this case is m minus n. So if we care about minus n, well, what does that mean? Well, it's the same length vector as n, it just is in the opposite direction. So if we start off, and we do care about the vector m, so we have our vector m there, or in fact, put the m here. All it means, instead of going up from the end of this vector, we're going to go in the opposite direction, but for the same length. So let's go to here, and that is the vector minus n. So if this is our starting point and we really care about this resultant vector of m minus n, that is going from here to here, and it will be a straight line. So that's going to be m minus m. Now, let's see if we can put on some of our points here. Had our m carried on and the n originally here, well, we know that angle was 30 degrees. Well, we've got opposite angles about a point here, so if this is 30, this angle between m and minus n must also be 30 degrees, so we can add that to our diagram. We also know something about the magnitude of m and the magnitude of m minus n. So we can add on the magnitude of m is equal to 3, the magnitude of m minus n is equal to 6. Now what does the problem actually ask us to find? The angle between the vector m and the vector m minus n. So in other words, let's call this theta there. Now, looking at the information we've got two lengths, an angle, and we want to find another angle. And that should be triggering to you with a triangle that we've got one of our rules. Now you've got the sine rule and you've got the cosine rule. Well, if you've got two sides and two angles, this must be an example of a sine rule problem. Now, with our sine rule problems, you want an angle opposite a length, an angle opposite a length. Let's look at what we've got. Well, the 30 degrees is indeed opposite the 6, but the 3 is opposite an unknown angle at the minute. However, if we can work out what this unknown angle is, as we have a triangle, then we can work out our missing theta. So we're going to find angle x first. Using the sine rule, we can say that we have sine x over its corresponding length, which is 3, is equal to sine of the angle that we've got, which is 30 degrees, over its corresponding length across from it, which is 6. So sine x is equal to 3 over 6, which is a half, sine 30. Sine 30 is also equal to a half, and a half times a half is equal to a quarter. So you sine inverse that, sine inverse of a quarter in degrees, 14.4775 degrees. Now I'm writing it to this level of accuracy because it isn't the final solution. Remember, we found this angle x, and that's between minus n and m minus n. That's not actually what we want. We want to find theta. So theta, angles in a triangle, 180 degrees, minus the 30 degrees, minus the 14.4775 degrees. So theta is approximately 135.5225 degrees. We can then look at the accuracy that they want to 1. That should be 1 decimal place. So to 1 decimal place, theta is 135.5 degrees to 1 decimal place. And if you want to just clarify that, we can say therefore the angle between the vectors m and m minus n is 135.5 degrees to 1 decimal place. And that's your final solution.